I just started the recording.
Hey, you can see my screen, right?
Yep.
Okay. Also use this. Anyways, welcome to, it's week 3. Welcome to week 3 of number theory. Today we're going over modular arithmetic. Last week we weren't able to do it, but this week luckily we're able to have a lecture now. Anyways, let me remove the annotation. Okay. As we saw in the first handout on our first week, recognizing divisibility, basically if a number is divisible by another, like how 4 is divisible by 2, it's essential to cracking many number theory problems, and you'll use it all over the number theory problems. But however, divisibility isn't usually enough to tackle harder number theory problems like the ones you see in AME, the middle late EMCs, and on some cousins reminders might even help you do the answer quicker. Like for easy cousins, you can, instead of bashing and dividing on long division, there can be tricks to find the reminders. Okay. What's a reminder again? I think we all know what a reminder is, but basically it's when you divide and then if there's some numbers left over, that's your reminder. So basically first we understanding the remainder when A is divided by B. So basically here we have gives more information than understanding whether A is divisible by B. So the remainder actually gives us a bit more information other than just saying it's divisible. So we can separate these remainder integers into set with a specific remainder when divided by 7. So here are the numbers when divided by 7 have a remainder of 0 for 14. Yeah, negative numbers also can be divisible by something. Negative 14 less than 0, of course. You'll see it with the remainder equals 0. 7, 14, 21, all multiples of 7 basically. Remainder 1, well, we'll tackle the negative part first, but note that this is when you divide by 7, you get a remainder of 1. See, 7 by 8. Yeah, you get a remainder of 1, you get a remainder of 1 as well. And then for negative numbers, you know that since negative 7 it has a remainder of 0, if we add 1, we get negative 6. And then while we can't do this, well, actually we can, but yeah, we'll go through, it'll be a bit confusing. So basically what I think of is that when we have to find the remainder of a negative number, I first find the closest number that's divisible by 7, aka has a remainder of 0, and then I see how much do we need to add to get to the other number, and since we add 1, the remainder is 1. Same thing for this, we add 1, the remainder becomes 1, and then we keep on doing for the remainder equals 2, 3, 4, 5, and here's 6, for example. All these are like 1 less before this because the remainder of 6, we can't have a remainder of 7. The remainder of the 7 is the same thing as 0. You'll see why later. And it should also make sense to you. This is all the indices shifted by 1 if we have a remainder set of 7. Anyways, even so we have 6, we have 13 because we did 1 remainder 6, 2 remainder 6, and so on. Same thing with these. If we classify whether we have it on divisible by 7, we only have 2 sets. It's not as very informative as this. All we have is just basically all the numbers divisible by 7, and this is just a set of all real all in natural and negative numbers, all integers, then such that and the numbers, well, Actually, I had to use modular arithmetic to divide. Actually, to make it make the definition of this set much more better. Actually, you need to use modular arithmetic, but for now we can just use words. X is not divisible. By 7. That's basically everything in this. And this is basically all the numbers divided by 7. As you can see, we all have these different sets, remainder 1, and this gives us much more information other than this. We only have 2 groupings, not as precise. So to introduce modular arithmetic, we'll take another look at the 7 groups of integers. Yeah, 0 through 6. 0 through 6, fairly in math, you might think that's only a total of 6 sets, but actually we have 0, 1, 2, 3, 4, 5, and 6. Because, and if you count them, you have to include this as well. So a total of 7 sets. So let's go save time by giving the name S subset I. We already learned this notation in the past 2 weeks, but basically this means remainder 0. This means the set of numbers with a remainder of 1 when divided by 7, and same thing like this. If it contains, yeah, basically that. Suppose we do that, we have an integer a. So we have a variable a that's an integer, and that exists in here. So it's here. Basically, yeah, I'll go a little faster actually, but yeah, we have set a. Why would the integer a plus b mean? Oh, we also have integer b in s equals 3, the remainder of 3. So it'll make sense if it's in set 4. If that's like, let's say we have 1, a is equal to 1, and it's in b as a remainder of b as a remainder of 3. Okay, b as a remainder of 3, that means b is equal to 3. 1 plus 3 is 4, and the remainder is 4. So we could say that this is true. So if a exists in set of 3 and b also exists in set of 3, then a plus b would exist in set of 6, because the remainder of 3 plus the remainder of 3 is equal to the remainder of 6. And if a exists in a set of 4 and b exists in set of 6, then the sum would exist in set of 10. But this is basically equal to set of 3, right? As 10 more than a multiple of 7. This is basically the remainder 3. See, like, so thus we can say S4 plus S6 is equal to S10, but it's also divided by 7, so we can subtract 7, we get 3. Then set of 3 is equal to set of 10 equals set of 17. Okay. Yeah, slow down on the chat. Try using direct messaging also, as I'm getting notifications, and it might even show in the recording. So, thank you. Okay. Oh. Okay, this is some like really early modular. Right? If a and b have the same remainder when divided by p, then they're interchangeable. This is might be a new word, but it basically means you can switch a and b around under addition. For now, it's only available when we do addition. We'll do it for the other operations later. Well, I don't think most of us know what interchangeable means yet, and it's best to learn with an example. So we can say, in other words, if we wish to compute the remainder when a plus b is divided by p, we can replace a and b by with the remainders. Let's call them R1 and R2 to supply the problem down to computing the remainder when R sub 1 plus R sub 2 is divided by p. That's basically what you're allowed to do. So let's do an example. Let's say a is 10, b is 17. We are dividing all of these by 6. Let's say p is equal to 6. Then we can say that if we want to find the remainder of this, we can simplify. We know that this has a remainder of 4, and this has a remainder of 5, right? And then these are the remainders, and then so if we add this, we get 9, right? and then 9 is smaller than 6, and we can also do this again. So since p is equal to 6, we have a remainder of 3, right? Because when you do 6 9, there's 1 remainder 3, right? That's a really easy example, but it'll help when you have like 5 digits, 6 digits, and a bigger device or bigger number p. So let's do this one exercise real quick. It is given that a and b have the same remainder when divided by 3. Why is a plus 2b necessarily a multiple of 3? Well, let's take cases. Let's say a comma b are in set of 0. Let's say this. So all of them are divisible by 3 by definition. So 0, and since we're using this, let's just say a plus b plus b. Since this, we can always go down to the remainders. 0 plus 0 plus 0 is equal to 0, right? So this is why. So therefore it's a multiple of 3. Then a and b is in set of 1. Then y is, then we can just substitute remainders. This is also 3, and that means it's also divisible because the remainder is 3 and we're dividing by 3. Finally, this, then we have 2 plus 4 is equal to 6. 6 is a multiple of 3, so if the remainder is 6, that means that's not for. So if the remainder is 6, that means these are going to still be a multiple of 3. And 0, 1, and 2 are the only 3 possible remainders. So there we are. So let's go to a first example. That was exercise. The Fibonacci series sequence has its first 2 terms equal to 1 and 1. That's implied that any term, yeah, you all should be familiar. Basically, sum of the last 2 terms is the next term. Neat. Okay, that doesn't matter. What is the remainder when 100 term is divided by 3? Once again, let's substitute everything to its remainders. When divided by 3, we get 1, 1, 2. The remainder here is 0. The remainder here is 2. The remainder here is 2. And the remainder here is, well, what we know is that we could still add, by the definition of Fibonacci sequence and how we use this fact here, we move. Basically, we can switch these numbers with its remainders, right? And by doing that, we can use the same file of the Fibonacci sequence. So we can add these 2 remainders. We did 4, and then when we divide by 3, we did a remainder of 1. 2 plus 1 is going to be 0. 1 plus 0, 1. 0 plus 1, 1. 1 plus 1, 2. And we continue this until we start seeing a pattern. So the 0, then we do 2, 2 again, 4, well, I mean 1. And kind of, as you can see, there's a pattern forming, right? 1, 1, 2, 0, 2, 2, 1, 0, 1, 1, 2, 0, 2, 2, 1, 0, right? So that's a pattern. Every 8 terms, the remainders repeat. Okay, so let's see if we keep on dividing by 8. Let's say 8, we know that 8 times 12 is 96. So before 100 term, so we know that 0 is going to be the 96th term. Then the 97th term is this, 97. Then this is going to be its 98th term. That was a comma. 99 and 100. And what does this say? This is 0, right? So therefore, we know that the remainder when the 100 term divided by 3 is 0. That's the answer. Now let's do an exercise. Compute this is a little bit harder, but it's actually not that pretty easy after we do the fact. Compute the remainder when 72 plus 79 plus 86 plus 93 all the way to 772 is divided by 14. Note that 72 has a remainder of 2, 79, well, yeah, we have a remainder of 9. And then 86, 14 times 6 is 84, we have a remainder of 2. 93, its remainder is 9. And then all the way to, well, 765. See that? We can multiply. 70, Yeah, it does oh, no, my pen's not working. Here we go. 70, then we have 56, right? Yeah. And then we have the remainder of 9. 772 on the other hand has a remainder of 2. Okay. And you can see it's a pattern of 2, 9, 2, 9 again, again. So first, let's see how many terms we have in the sequence. So we can say that since each number, it's an arithmetic sequence, with A1 is equal to, so we can use the arithmetic sequence formula, which is, well, yeah, we can use the arithmetic sequence formula, but another trick is that we know that the divisor, the common divide, well, I forgot the name, but add by sevens, it's the common difference. I'm sorry, I messed it up with the divisor. So, and then if we make this 7x, let's say that the total, when you have two terms, you increase by 1/7, so that means x is 1, and then we have to remember to add 1 on the end to get the total number of terms. So we know x is 100, so therefore that's going to be 101 terms, because there's a total 100 leaps of 7, right? And then for each leap of 7, there are two numbers, so we have to like account for one more. So we can also use the formula, but this was using, this is a little bit quicker. So 101, that's going to be 101 terms. We know this ends in a, we can call this the even remainders and the odd remainders. So we know that there's going to be one more even remainder because we have an ending 2. So we can say that, so this is term, let's say this is term 1, term 3. This is going to be term 101. So all these terms, that's going to be a total of 51 terms, right? So 51 x2, because we are computing the remainder, so 51 times 2, and then we have 50, because 101 minus 51 is 50. 50 remainders of 9, right? Let's multiply out. 102, 450 is equal to 552. And if we divide this by 14, we are basically done. And we get a remainder of 6, and that's our answer. Right. So basically what we did was we first we placed all these numbers with its remainder, we found a pattern, then we found how many terms are in this arithmetic sequence, and then we found that there's how many 2s and how many 9s there will be, and then we added it up and divided by 14. And this is why we start with the modular notation. So basically we write A is congruent to B modular mod Q. Sorry. If and only if A and B have the same remainder when divided by Q. So if A is 3 and B is 6, and then let's say Q is equal to 3. Okay, so we can say 3 is congruent to 6 modulo 3. If and only A and B have the same remainder when divided by Q. In other words, when Q divides A minus B, and A minus B is -3, and we know that 3 divides -3, right? Yeah, so that's basically modular notation. So we can say that 3 is congruent to 10 mod 7, as -7 is congruent to 0 mod 7. And here's a warning. We need to know that mod p is not an operation. It won't make sense to define a function. Right? This is algebraic. It's still better to know this warning. Fx is equal. This is not a function. To assume that fx outputs the remainder and x is divided by x. X is divided by 8. That's not a function. The symbol mod p is only used to signify the sets si, as we learned earlier, we are using. When writing out Scratchwood, it's fine to treat it as its own operation. And then guess what? We got another warning. Yeah. It is the case that 2 is congruent to mod 5 mod 3, right? Yeah. So it seems it makes sense that you can interchange them under all contexts of modulo 3. This is true in the case of addition. You can do this as we cancel, you just 0. So basically, if we let a is equal to 1, we know that 3 is congruent to 6 mod 3. If we let a is equal to 2, then we know 4 is congruent to 7 mod 3. We can say that that's possible. However, the thing is, it's not true for every single operation. Let's go to exponents. So we know that 2 to the power of 2 is congruent to 25, right? 2 to the power of 2 is congruent to 25 mod 3, which is congruent to 1 mod 3. 2 to the power of 5 is congruent to 32, which is also congruent to 2 mod 3. But we know that we thought that 2 and 5 were allowed to use interchange. It's interchangeable under all mod 3, right? But guess what? It's not, because exponents, it won't work with exponents. So basically, even though 2 is congruent to 5 mod 3, 2 to the power of 2 is not, means not congruent to 2 to the power of 5. Basically, we can substitute numbers with unknown numbers coming with them whenever we choose. But no, it works. It's interchangeable under addition, subtraction, and multiplication. Division is going to be a little more tricky than that, and we'll cover that later. But what you need to know is that exponents, it won't be always true. So it's best not to do. You can't do this with exponents. In other words, okay. Basically, yeah. Basically here you can basically cross this out to make it. Basically, we're just saying 2 to the power of 2 is congruent to 1 mod 3, while 2 to the power of 5 is congruent to 2 mod 3, even though these two are congruent. That's basically what we're saying. Okay. And here's another fact. Well, for now, it's best to know that for any prime number p, any integers a and b, and then we have the word again. We have the coprime, relatory prime. We all know what it means from the first week. There exists a solution to the modular congruence. Modular congruence ax is congruent to b modular p. So basically, if p is prime, p needs to be prime, and a needs to be coprime to p, and b can be anything. So let's do an example. 3x is congruent to 5 mod 7. Basically, what this says is that's going to be a solution x. That's going to be a solution x to this equation. Well, it's not an equation, it's a congruence. Let's go be an x that satisfies this. And actually, if x equals 4, it works. So, and that's also going to be more solutions, because and that's also be more solutions, like x is equal to 11. Someone on Andrew, I'll ask you again not to play the call. If we do it one more time, I'm gonna put you back in the waiting room. Okay, we're banning you. Goodbye. Sorry about that. So basically, the solution is x is congruent to 4 modulo 7. And if we keep on trying all values, basically this means x is congruent. X can be 4, 11, 18, 25, and then like say it's 75. 75 is congruent to 5 modulo 7, because 7 times 10 plus 5 is equal to 25 times 3. And then we have another question. When does, let's say that b is equal to 1. When does ax congruent to 1 modulo p have a solution? So let's take two examples here. Let's find if there are any solutions to x. 3x is congruent to 1 mod 6. What does it mean? That means 1 mod 6 is basically all the numbers 1, and also its negative counterparts, basically We have a question. What did it say in the last part? Here. Pan out. Basically here, basically it said AX is kind of, that's going to be, well, for any prime number P, when P is prime and with A co-prime to P, relatedly prime, in other words, then we can always say that the X is a solution to the modular congruence. AX is congruent to B modulo P. And then you'll learn it more when we get into examples, which I have like a few of them later. So yeah, keep it open for continue reading this. And what I said here is that X is congruent. I just made a solution up, like if X equals 4, then this congruence is true because 12 is congruent to 5 modulo 7. And you can also try all these values out for X and see how it works. So when does AX is congruent to 1 modulo P have a solution is what we're working on. So we are trying to see if that's going to be a congruence X here for this congruence. So anyways, we are trying to find a solution. So this basically says that X can be 3X is congruent to 1. Well, basically, 7, we can always write this as 7 mod 6. We can also write this as 13 mod 6. Basically, when this is divided by 6, that we need to have a remainder of 1, right? That's basically what it says. But I'm going to say that that's not going to be true, actually. Why? Well, we can move this to the left-hand side. Let's subtract 1 because we said that we are interchangeably, it works for subtraction operations. So we did 3x minus 1 is equal to 0 modulo 6. Think about this for a second. We know 3 is, 6 is divisible by 3, right? So let's just try some values of x, 1, 2, 3. Can you see when x is 1, you get 2 is not congruent to 0 mod 6. If we try 3, we get 8, which is not congruent. Now I like to say that 3x minus 1 is basically every number that has a remainder of 2 when divided by 3. I like to say that. Now think about it. In other words, that means if we take it divided by 6, well, divided by 6 it makes it a little bit tricky, but yeah, it's basically just 2 mod 6 and 5 mod 6 because we try different values of x. But basically what I'm saying is 3x minus 1 is congruent to 2 modulo 3. So that's and then that means if we since there's always -1 and 3 is a factor of 6, and we are basically saying one less than a multiple of 3. 1 less than a multiple of 3 is basically going to be the remainder of this is going to be 0. But can you find any numbers? That actually satisfy this? Because basically we are saying that, well, you could just start trying the values of x. We know that we can't make any numbers, and if we have like any number in the form 3x minus 1, it will not be divisible by 6. Well, this is a bit hard to understand, but what I'm saying, if we multiply, since multiplication is allowed, right? If we multiply both sides by 2, we get 6x is congruent to 2 modulo 6, right? And then when we subtract 2 from both sides, we get 6x minus 2 is congruent to 0 mod 6. What does this mean? It's saying that 6x is congruent to 2 modulo 6. How I don't think this makes sense, does it? Why? Because this left-hand side is being multiplied by 6, right? So it should always be 0 mod 6. But it's saying 6x minus 2 is going to be congruent to 0 mod 6. Obviously, this is a false statement. We have to add strikes. So that means if this is false and this is derived from this, it means this is also going to be false, right? So therefore, if this is false, that means there's not going to be any solution x such that 3x is congruent to 1 mod 6. Well, nothing integer solutions. We'll talk about them. Fractional solutions, but for now we are just focusing on if x is an integer. Let's go to a second example. Let's erase some stuff. Basically, what we did was multiply, so the left-hand side will have a 6 multiply, and then we showed that this statement was not true. Therefore, that's and since we derived it, that means the former statement won't be true either, since we did doing mistakes with the calculations. Right, so let's get on with the next example. So it only works if A and P are coprime. Yeah, that's basically, you basically said it correctly as here. So, and since for A, B is allowed to be anything, and if we let B is equal 1, we know that A needs to be coprime to B. And that's why I'm trying to show them with examples. So congratulations, you're one step ahead. So 4x is congruent to 1 modulo 7. Let's try this. Basically, 4x minus 1 is congruent to 0 mod 7. So therefore, we are saying that that's going to be some value of x such that 4x minus 1 is a multiple of 7. Right? Well, let's just try some values. Let's try, you can say that 8. Let's try if, well, we can try 7, 14. Let's see what happens when x is equal to 2. 4 times 2 is 8. 8 minus 1 is 7. And is 7 congruent to 0 modulo 7? Yeah, it is. Right. Let's find another one. How about we try x is congruent to 9, because 2 is congruent to 2 mod 7, right? So, and then that also means this is also 9 is congruent to 2 mod 7. So let's try x equals 9. So if we try x equals 9, well, we have 36 minus 1. 35 is a multiple of 7. So we can say the answer is all numbers of x such that it's 2 modulo 7. But are we sure that that's not going to be any other solutions? Well, we can try all other modulo. Let's say x is equal to 3, 3 modulo 7. It doesn't work. X is congruent to 4 modulo 7. If we try 4, it won't work. If we try 5, it won't work either. If we try 6, it also doesn't work. And if we try 7, it doesn't work either. So it only works for 2 modulo 7. That's basically what I'm saying. So therefore, that's our answer for all numbers such that x is congruent to 2 modulo 7. And see, this has a solution. This is a solution. And why does this have a solution? Well, we basically are saying that this is A, this is B, and this is P. Note that how GCD, the greatest common GCF, the greatest common factor of 4 and 7 is equal to 1. That means they're coprime, right? And then how we have a solution here? Well, the proof is going to be a little bit rigorous, but it should be intuitive. Like we are saying that 3 and 6, just multiply this by 2. Okay, just multiply this by 2 and you see this is already a false statement. Why? Because 3 and 6 are not coprime. So basically for now, as long as A and the P are coprime, you will always have a solution, at least for integers. Yeah, you'll always have an integer solution. So this basically sums it up. This is the same thing as saying that this is coprime. So basically the congruence AX is congruent to B modulo P has a solution of GCD A and P is equal to 1. Okay, we have another text box here. Okay, now we are going to talk about modular inversion. Yeah, this is kind of hard as well for me when I started learning number theory. So basically we express the modular inverse of all modulo p as r to the power of -1. For now, so that r to the power of -1 is a solution to rx is equal to 1 modulo p. Oh, we forgot another line here, I think. Rx is congruent to 1 modulo p. So basically, we're just saying for all numbers such that x is equal to r -1, r -1 is going to be a solution because r times 1 over r is equal to 1, right? No matter what, it's still going to be 1, and p is an integer. Oh, yeah, we can see that. So r times 1 over r is equal to 1. So they call that, we know the modular inverse r -1 modulo p is only defined when GCD r and p is equal to 1. Otherwise, it cannot. There's a chance where r to the power 1 can also be 1 over 0. Yeah. So basically, we're just limiting such that r and p are relatively prime. So this is only defined when r and p are relatively prime, as we talked before. So let's try an example. It's given that 48 to the power of -1 is congruent to 1 modulo p for some prime with 48 to the power of -1 defined. And since 48 to the power of -1 is defined for some prime p, that should mean, what should that mean? We are trying to find the value of p. So first, let's write down an equation. If let's say r is equal to 48, so GCD, since r is equal to 48, not r to the power of -1, this is r, GCD 48 since therefore GCD 48 p is equal to 1, right? So we're trying to find the value of p. So basically we're finding a number p such that GCD 48 p is equal to 1, and this is a true statement. Well, how about that? So it is given, so we know that all is 48. R times x, which is equal to this, is congruent to 1 modulo p. And then we are saying that, p can be equal to 47. Why? Because 47, 1 modulo 47 can be either 1, 47 plus 1, which is equal to 48. And this is 48, right? So we are saying that the modulo inverse 48 to the power of -1, which is congruent to 1 modulo p. Basically, we are saying that p is equal to 47. If we try here, GCD 48 and 47 is equal to 1. And also, I think, well, I don't think we need to say the smallest value of p. I think the only solutions would be 48. Well, I think we I think we have to say the largest value of p to make it. Yeah, what is the largest value of p? So 48 to the power of -1 is congruent to 1 modulo p, is what we're saying. Okay, and then we are once again, it's a little bit confusing. So we're saying all this 48, right? The modular inverse of 48 mod p is equal to 48 -1. This is such that r -1 is a solution to r of x is congruent to 1 modulo p. 48 times 48 to the power of -1 is equal to 1, which is congruent to 1 mod 47. And we also know that GC 48 and p, when p is 47, is equal to 1. So that's why we're allowed to use that. Well, it's almost 2, so we can take a 5-minute break if that's fine. And then we have a good few amount of examples, so let's take a 5-minute break. And then at 1:55, we're continuing. Okay, let's continue. So let me share my screen. Okay. We are on example 3.11. What is the remainder when 4 or 5 is divided by 7? Well, for this question, I like to think of benchmark fractions, basic fractions whose numerator is 1. I think this 4, we should take out this later because r to the power of -1 is going to be equal to 1 over r, and 1 over 5 is equal to 1 over r if we let, so we can let r is equal to 5. And then by a definition of modular inverses, we are trying to find the solution x such that 5x is congruent to 1 modulo p, and our modulo here we're dealing with is 7. So let's do some Gaussian check. So x is equal to 1 modulo 7. Well, let's start with x equal to geo modulo 7. 5 times 0 is 0. 5 times 1 is 5. 5 is not congruent to 1 modulo 7. 5 times 2, 10 is not congruent to 1 modulo 7. 5 times 3 mod 7. 3. When x is equal to 3 modulo 7, we have x is equal to 3. We can try 5 times 3 is 15. And then 15 is congruent to 1 modulo 7, right? Therefore, that's a solution. And that's going to be one solution. If you want, check for yourself, you can try 4 modulo 7, 5 modulo 7, 6 modulo 7, and so on. But this is the only solution of x. So therefore, r to the power of -1 will be congruent to 3 modulo 7. Right? Okay. See if I'm not making any mistakes. So basically, R1 is equal to 1 over 5. 1 over 5 is congruent to 3 modulo 7, and that's a true statement. What if we multiply both sides by 4? Because we want to change it back, right? Right? So that means 4 times 1 over 5 is equal to 4 over 5. And congruent to 4 times 3 is equal to 12 modulo 7. And note that we have remainder in quotation marks, because it doesn't make any sense to divide something and find the remainder of a fraction. But if you're just finding its modulo remainder, we can say. So, and then 12 modulo 7 is congruent to 5. 4 or 5 is congruent to 5 modulo 7. And therefore, remainder, note in quotation, is equal to 5. That's answer. Our Zoom is being laggy. Well, what usually I do is check my internet connection, but I can go over again. Okay. Okay. And if it's laggy for you, you can always see the recording. So, but I'll still go over when you rejoin. See the participants. Let's see. And also at this point, we are pretty much almost done. Actually, we only have the waiting room. Yeah, we're pretty much almost done. We already went through addition, subtraction, multiplication. What we're doing now is basically division, because this is a fraction, right? So we're going to the operation of division, and we're going to go through a little more about it. So for today, I understand. I'll possibly so basically we just multiply by 4. We know the motivation is because benchmark fractions, because r to the power of -1 is equal to 1 over r. That's basically why I wanted to make it a benchmark fraction and multiply it by 4 at the end, because of this, the definition of algebra. So then we can substitute r is equal to 5, right? And therefore we did this modular equation, and then we solve for x, and then we go back here and plug it in using knowledge of modular arithmetic, and then we end up multiply everything by 4, and then we get the answer. So that's enjoying it, so I'll go to the second. But if Zoom's being laggy, you can always see a recording, and I think the recording should work. Yeah, the recording should be laggy. Is the recording still on? Yeah, this. Solve the following. We have 4 congruents. Solve the following congruences for x. 4x. Work is congruent to 8 modulo 37. That's your first cousin. Well, division is going to be really wonky. So there's always going to be sometimes you can use it, so times you can't. So I'm going to do subtract. I'm going to subtract everything by 8. Okay, 0 modulo 37. We're just trying to find x such that this is a multiple of 37. Right? And then we can factor this. 4x minus 2 is congruent to 0 mod 37. And then note that 4 doesn't have to do anything with 37. 4 and 37 are relatively fine. So we could just like not care about this. And then the only way for this to be 0 modulo 37 is for x minus 2 to be congruent to 0 mod 37. Because 4 can't do anything about being 37 is prime. 4 is not close to being a factor. Close to being a factor of 37. So basically all we have to make sure is x minus 2 is congruent to 0 modulo 37. So if you add 2 with it, x is congruent to 2 modulo 37, and that's an answer. That's a first answer. Okay. I don't think I have enough space, so I guess I have to erase. But yeah. As we saw, basically we found that 4 can't do anything about whether x minus 2 is going to be divisible or not. So yeah. So we have to focus on x minus 2 instead. But the second one is going to be a little bit trickier because 4 and 38 are not related fine. Once again, I want to subtract first. Factor 4x minus 2, but we can't do the same thing as we did last time because 4 contributes a factor of 2 no matter what. 2 times 2 x minus 2, and then we know that mod 38 is equal to 2 times 19. So no matter what, this will always have a factor of, well, this will always have a factor of 4, but we all know that it still contributes a number 2. So first of all, it's best to explain. Let's do it what we did last time. Let's assume that 4 doesn't matter. Then we did x minus 2 is congruent to 0 mod 38. And then therefore x is congruent to 2 mod 38. That is a solution, right? And we could just say we're done, but are sure this is the only solution? That's the problem. We're not sure that it's the only solution. We know there'll only be one solution when this is co-prime, when these two are co-prime, but these two are not. Well, what should we do here? Well, basically, we also have to note that this contributes a factor of 2. Therefore, yeah. We are saying that another solution is congruent to 2 modulo 19. I'm proposing that this is also another solution, is what I'm saying. Right? If we try 21 here, we try 21, 19 times 4 is 76, and 38 times 2 is 76. So what did we do wrong here? Why is the solution not just 32 modulo 38 anymore? It's oh, I don't know why Milo keeps on doing this. I'm doing something. So once again, 2, we can write this as 2 times 2x minus 2. So what we're saying that always this contributes a factor of 2. So no matter what, it's and then we can also just divide this by 2. Why? We divide by this by 2. We know you can usually not divide modulos, but for this we are saying that all numbers are still go have a factor of 2. For a number to be a multiple of another, we already learned that it needs to have this in its prime factoration and anything else. This is the bare minimum. We are saying that this is its bare minimum. Okay, so so we can all make this into 0 modulo 19, and then we have 2x minus 4 is congruent to 0 mod 19, and 2x is congruent to 4 modulo 19 by adding. And then finally, we can say that when x equals 2, it works. 2 when x equals 21. Well, yeah, when this can be 42. So when x equals 21, it also works. When x equals 40, it also works. You can try it. Basically, what we're saying is that the answer is 2 modulo 19. Yeah, 19. That's our answer. It's not 2 modulo 38 only, but it's also 2 modulo 19. Because we are saying that 4 and 38 GCD of 4 and 38 have a factor of 2. So no matter what, the left hand will always have a factor of 2. So we can simplify this problem into 38 over 2, 0 modulo 19, as we're dividing by its GCD. So that's basically what we did. Okay, for the third question, we're trying to say that find the x, that's 6x is congruent to 10 modulo 15. Once again, we subtract, modulo subtract, and then we factor. And then this time, 2 and 15 are coprime. So that means 2 and 0, well, 2 and 15 are coprime. So this again doesn't matter when we're trying to solve. So we need 3x minus 5 is congruent to 0 modulo 15. We are finding a solution for that. 3x congruent 5 mod 15. And you saw me do it last time, but once again, we can guess and check. So keep on doing all numbers mod 15. So try 0 mod 15. Try 0 mod 15, 1 mod 15, 2 mod 15. It's only 14, 15 numbers. So we can always do that. And then, we can also restrict it to, well, actually you can, but basically we can restrict it to all numbers that ended 5 or zeros, right? Because it's mod 15. So what if we try 10 mod 15 doesn't work, 5 mod 15 doesn't work, but how about, and then it's also possible if that won't be a solution sometimes, but I think that should. Yeah, there's actually no solution in this case. That's usually pretty bad, but let's not do that. But we can't find anything mod 15, right? So let's see, what do we do anything wrong, or is this just like a coincidence or something? But however, but what we did wrong here. Let's see what we did wrong here. Let's go back to this equation. 15, 3 is a factor of 15. So we're saying a factor of 3 times something minus 5 is going to be 0 modulo 15. And we know that 5 is congruent to 2 mod 3. So we're just saying that x, we're just saying this expression, which is congruent to 1 modulo 3. We're basically saying this number, which is 1 modulo 3. And 1 modulo 3 is basically 4 mod 15 is the same thing. It can be 4 modulo, x can be 4, x can be congruent to 4 modulo 15, x can be congruent to 7 mod 15, it can be congruent to 10, can be congruent to 13, can be congruent to 1, can be congruent, yeah, it can also be congruent to 1. But 0 is not found anywhere. It's basically just 1, 4, 7, 10, and 13. 0 is not there. Therefore, we have no solution. gonna have what happened along is that we did a correct method. We know that these are, well, yeah, we know that these two are actually not related prime, but still we factored and tried to find a solution, but we couldn't find any. So that's what will happen. And then sometimes that does go be a solution, but other times that won't. So basically you just have to test all the modules. Finally, let's try this question. We move 42 to the left-hand side and we make it congruent to 0 mod 126. Some pretty big numbers, but still factorable. And divide by 2, oh, it's divisible by 14. 14, 2x minus 3, congruent to 0 mod 126 is equal to 2 times 7 times 9, right? No, 2 times 7 is covered here. Anything is always go have 2 times 7. So we can simplify this question into 2x minus 3 is congruent to 0 mod 9. And we are supposed to find a solution. We are finding a solution. 2x is congruent to 3 modulo 9. And we are saying that the answer is going to be x is congruent to 6 modulo 9. And try it. And when x is 6, we did 12, which is congruent to 3 modulo 9. 15 also works, right? So, and if we try any other modulo, if we don't find it here, being congruent to 3 modulo 9. So this is going to be our only solution, right? Make sure I didn't. Yep, our only solution is 6 modulo 9. And we're done. Okay, this is going to be a little more. When are we allowed to divide? Well, this is going to be a little confusing. We are allowed to divide when, well, I think that's going to be a factor. Oh, what do we do? There should be, okay. This is bit, let's jump here for a second because I think I could have taught this earlier. Suppose we wish to divide both sides of a congruence by some number a. So after dividing both sides of the congruence by a, we might need to change the modulus. So usually we are always allowed to divide actually, but there's some special cases actually. There's going to be some cases where you also have to divide the modulus by itself. So let's see when we're trying, for now we're trying to find when we can divide, when we have to divide the modulus. So in other words, I'm saying that we can always divide, but sometimes to make that operation valid, we also have to divide the modulus as well. So suppose both sides of a congruence have a common factor g. So g is its common factor. Then it'll look like this. And if GCD g and p is equal to 1, this is again saying that the common factor is co-prime. So basically, it's what I said before. I'm basically saying that the common factor is going to be g, and then g and p must be co-prime, so we can divide. And when it's not co-prime, I think we have to divide by g on the modulus as well, but we'll go through that later. So if GCD g and p is equal to 1, then we are allowed to divide both sides of the congruence by g, just as we did in algebra, like on an equation. Okay, which of the following congruences have a solution? Once again, we do the same thing as we did back in the last example, but some of these may not even have a solution. So that's a twist. Well, let's see if we have any solutions here. We are basically saying that a number which is 1 modulo 4 is going to be congruent to 2 times 27. Is this true? Well, it'll look pretty hard actually. Am I on that? Yeah, it'll look pretty confusing to try doing this. Try bashing every single modulus 54, but basically I'm saying that I did. No, I didn't. Okay. So let's start trying something. Let's try. Okay. First of all, we are noting that let's look at whether it's even or odd, which is usually what I do first. We know that since this is even and we are subtracting by an odd number, we know that this is going to be odd. But however, this is even. Any 54 times 1, whether if we multiply an even number by an odd number, no matter what numbers they are, you'll always get an even number. So therefore, this is basically saying all even numbers. But 4x minus 3, if we put any integer x, any positive, well, you can also do negative numbers as well, but you'll always get an odd number on the left hand side. An odd number is never equal to an even number, right? So therefore, there's going to be no solution. No solution. Let's go to a second one. Here we can actually use the division thing we just learned. 7, both of these have a common factor 7, and 7 and 25 have a GCD of 1. Therefore, we can divide by 7, giving us x is congruent to 2 modulo 25. And that was really quick. We just got a solution. X is congruent to 2 modulo 25. And we did nothing wrong here. 7 and 25 are co-prime, so there shouldn't be another solution. And just in case you want to check, now let's do that. But you just had to try every other modulo of 25, which will take a while. So this is an example of where we can't divide without changing the modulus. But for now, let's act like we don't know that we can change the modulus. For now, let's just do what we did. 4x. First of all, I think it's best if we see what happens if we divide both by 4, right? We divide both by 4. The x is congruent to 3 mod 24. Now we'll hold this. We'll see why is this not the only solution. Okay, let's do a subtraction and factorization. If we do that, we did 4x minus 3 is congruent to 0 mod. Oh, that looks good. Yeah, congruent to 0 mod 24. And we know that always it'll give us a factor of 4. So that means this must be a factor of 6, right? Because 4 times 6 is 24. So this must be divisible by 6. So in other words, x minus 3 is going to be congruent to 0 mod 6. Therefore, just means that it implies it. Therefore, with the x is congruent to 3 modulo 6. And that's an answer. It's not 3 modulo 24 anymore. It's not 3 modulo 24. 3 modulo 6 is much more broad. And 3 mod 6 covers all the solutions. So that's an answer. That's an actual answer. 3 mod 24 is only part of the answer. But you're supposed to find all solutions. So if we did that, your answer will be wrong. Because you're not saying in that's not all your solution. Here's another example. When we can't divide by 3 again, because sadly modulus is divisible by 3 as well. So we have to do the old fraction. Well, it's not old, but it's actually still a good method. But all you have to do is subtract, and then you have to like just try different type of modulus at the end. But it still works pretty good. What I'm doing again is just we are subtracting, moving everything to the left hand side. Then we factor. We know that since this is a 3 and this is 3 times 8, this must be divisible by 8. So 2x is going to be congruent to 3 modulo 8. Yes, just step that, but I think you'll understand. 3 modulo 8. And let's see this. 3 modulo 8 can be written as 8k plus 3. Because basically k can be any integer, because this is the form of all numbers in the set that has a remainder of 3, right? Because 8 is congruent to 0 mod 8. So this will be 0 plus 3 is congruent to 3 mod 8. Anyways, but this will always be an even number no matter what k you use. This is an odd number. If you add an odd number to an even number, you get an odd number. And so therefore this will always be odd. But here we are multiplying by 2. And since we're in the set of integers, for any x we use, this will always be even. And we already said an even number can't be congruent or equal to an, well, it can be congruent, but it won't be equal to an odd number. So this will always be an odd number. Basically, we're saying that 2x needs to be congruent. The 2x needs to be odd. It's basically a way to say this. But 2x can never be odd, no matter what x you use. So there's not going to be any solution. So this does not have a solution. This does. This does not have a solution either. These two does have a solution. So that's an answer. Okay, let's finally go to when what happens to both of them when P GCD G is equal to, when the common factor is going to be the GCD of A and P. So after dividing both sides of the congruence by A, we might need to change the modulus as well. If G is equal to GCD of A and P, then we want to divide both sides of the equation by A. We also need to divide the modulus by the greatest common factor. In particular, if G is equal to GCD A and P is equal to 1, then the modulus does not change. So we can use a lost example here. Let's use, which one was it? Yeah, let's just do not the lost, the next lost event. 4 is equal to 12 mod 24. We want to divide by 4, right? Correct. We want to divide by 4. And since 4 is going to be a and then P is going to be 24. GCD of 4 and 24 is equal to 4, which is equal to G, right? So G, we also need to divide the modulus by G. So let's divide everything by 4. 4 is congruent, I mean of the non-modulus. And then here we have to divide by G, 24 over G, which is equal to 4. So with it, X is congruent to 3 modulus 6, right? And that's what we got here as well. And I think in the handout there's also an example. I think we can use that. Let's go to that. Let's do these two. The other ones can still be solved using this method. Yes, I know how to copy images. Okay. Oh, well, it was already there, so that's good. Okay. Okay, this is a lost exercise. So basically, let's use a fact. 4, if we want to divide by 4, then 3 mod 14 over GCD of 4 and 14, right? That's, we're just using a fact, right? Yep. And then with that, X is congruent to GCD of 4 and 14 is equal to 2, 14 divided by 2, 7. And there we go, our answer. That's in Control G, though it needs to eraser. Okay, second question. Here we want to divide by 2 because 8x and 8 and 6, right? If we divide by 2, we get 4x is congruent to 3, and then we get modulo 16 over GCD. We're dividing by everything. We divided everything by 2, and we have the original number that, right? 16. So 4x is congruent to 3 modulo 8. As you can see, this is even. This is saying that it needs to be an odd number. Therefore, there's no solution, right? Right. This will always be even. We're trying to this. This is basically the set of all numbers that are 3 modulo 8. So all the numbers in this set are going to be odd, but this is an even number, so there's no chance of it being in this set. So there's going to be no solution. Next, we want to divide by 5 because we can divide 5. X is congruent to 25, I note that since GCD 5 and 17, they are coprime, so we don't have to change the modulus. Don't do anything to modulus, right? So x is congruent to 8 modulus 17. And our final question, we can divide everything by 7 because all 21 to 8 has a GCD of 7. So 3x equals 4 modulus 35 over GCD of 7 and 35, and that's equals 7. So and then for now we can, and if we just do some eyeballing, and if we just Gaussian check some values of x, we see that x is congruent to 3 mod 5 works, right? And you can try it for yourself. 3 mod 5 works, and that's a solution. So yeah, we are done. So just in 1 hour, 1.5 hours, we went through the basics of modular arithmetic and modular inversions. Where can we do the? Yeah, sure, I can do it. I mean that's my ratio. And if we have any internet problems, the recording, I'm happy to redo the problem for anyone. But if you have any problem, if you like want to review the handout, review the lecture when you're doing the handout, you can always see it on a YouTube channel. It takes like 20 minutes for us to sometimes a few hours to post it, because Zoom sometimes doesn't work. So here we have 4x is congruent to 12 mod 14. We see that we can divide everything by 4. Right? We want to divide because 4 GC 4 and 12 is equal to 4. Where if we divide everything by 4, the x is congruent to 3 mod, and then note by a fact, as we saw the fact, note that 14 over GCD 4 and 14, because we are trying to divide everything by 4, we have to take GCD at the bottom. Then we get x is congruent to 3 modulo 14 over 2, because GCD 4 and 14 is 2. So x is congruent to 3 modulo 7. And that's an answer. Okay. Well, other than that, I hope you all enjoyed today's lecture. Yeah, no problem. And then yeah, we'll see you next week, and expect our last lecture is going to be on the 19th, and most of us have school, so expect like the last lecture to be a little bit late. But for now, it's really matter, as if we can't attend it, that's totally okay. As you have the Discord office hours, and you can just ask anytime as well. But yeah, if you can't attend, that's still totally fine. Anyways, thanks for coming to today's lecture, and I'd like to see you all next week.